Welcome back. In this example 6, we want to find the volume of the solid obtained by rotating the region between the curves y equals x cubed and y equals square root x. So the same region as in the previous problem, but now you want to rotate it about the y-axis. All right. We have already seen in our previous example, the intersection points are 0, 0 and 1, 1. When you rotate it about the y-axis, notice you get a solid that is like a cup minus take away, that is a pit like that. So the solid part is here and inside there is nothing. So because we rotated about the y-axis, your cross sections are going to be horizontal. Width of each cylinder now is delta y. In other words, this tells me that we are going to take integration from 0 to 1 on the y-axis. So the solid is supported on the vertical axis on the interval 0 to 1. That's the y-coordinate 1. The width of each thin cylinder is delta y. The base of each thin cylinder is the region between, there is an outer circle and there is an inner circle. So region between two concentric circles. The outer circle has radius. Well, let's look for the radius. Now, outer circle is this horizontal distance. So that horizontal distance is what we call x coordinate. This curve, x coordinate, well, that curve is y is x cubed. So x coordinate is cube root of y. That's the outer radius. What's the inner radius? That's the x coordinate of this curve. That curve is y equals square root x. So x is y squared. Okay. So area of that washer, that is the region between the outer circle and the inner circle, is pi outer area squared, outer radius squared minus pi inner radius squared. So you're going to take this area of the base times its width. So when I take the integration, my volume of the solid is integral 0 to 1 pi y to the 2/3 minus y to the 4th dy. So at this point, pi is a common factor, it's outside. Integral of this particular factor is y to the 5/3 over 5/3 minus y to the 5th over 5. Limits of integration are 0 to 1. So all I need to do is substitute y equals 1, 3/5 minus 1/5, that is 2 pi over 5. Okay, cube units. All right, so this was the case where you took this region, rotated it about the y-axis. Now here is another setup. Find the volume of the solid. You take the same region, rotate it about the line x equals 2. Notice x equals 2 is the vertical line here. So now we are not rotating about the x-axis or the y-axis. We are rotating about this particular line. So you take this region and rotate it about this particular line. Now we already know the points of intersection for these two curves, 0, 0 and 1, 1. So when I rotate it about this particular line, I get a solid which looks like this. I took that curve, rotated it about. You see, it's like a strange looking donut, if you like. Okay, it's one connected piece donut with a big hole inside it. All right, this curve is y equals square root x. This curve is y equals x to the power 3. Now, because I have rotated about a vertical line, my cross sections are horizontal. You see, my cross sections are horizontal, and each cross section is is uh, is the region between an outer circle and an inner circle. So to summarize, this particular solid is supported on the y-axis, that is the vertical axis, from 0 to 1. That's the highest y. The thickness of each cross-sectional cylinder is delta y. The cross-section for each y, when you take horizontal slices, is the region between two concentric circles, right? There is an outer circle and an inner circle. Now, what is the outer circle? Well, I'm going to measure the radius from here, from the center. So if I go to the outer circle, what's that radius going to be? Well, here is 2. So from all the way to 2, the entire distance, I'm cutting away this much distance. And that was the x coordinate. So from 2, I'm taking away x coordinate. So this is, you have to be careful here. So this entire length is all of 2 minus that small distance. That small horizontal distance is actually x coordinate. You see, horizontal distance from here to here is x coordinate of that curve. So y is square root x. So x is y to the power 2. So 2 minus x is 2 minus y to the power 2. So that was the outer radius. What about the inner radius? Well, by the same argument, the entire distance from the x equals 2 line to y-axis is distance 2. I need to take away x coordinate of the inner curve. So from 2, take away x coordinate of the inner curve. Inner curve is y is x cube. So x is cube root of y. That's the inner radius. So what is the area of the region between two circles? Outer circle minus inner circle. Outer circle has area pi 2 minus y squared power 2, because that was the radius squared, minus the inner circle has pi, its radius squared, and its radius is 2 minus cube root y. So volume of the solid will be integral 0 to 1 ay dy. Okay, I hope it's clear, because these are horizontal cross sections going from 0 to 1. So ay dy. So ay is all of this, right? So notice pi is a common factor. You bring it out, and these are complete squares. So you need to use your formula. 2 squared minus 2 times y squared plus y to the power 4 minus 2 squared minus 2 times cube root y plus cube root y squared. So notice we have written it in terms of powers. Simplifying, the 4's cancel. So these ones survive. Negative 4y squared plus y to the power 4, positive 4y to the power 1/3, and negative y to the 2/3. When I take antiderivative, this fetches me negative 4y cubed by 3. This fetches me y to the 5th over 5. This fetches me y to the 4/3 over 4/3, and that 3 times 4 is a 12, minus this fetches me y to the 5/3 over 5/3. At this point, all we do is substitute the limits. Limit y equals 0 gives me 0, so it's only y equals 1. Substituting y equals 1, I get negative 4/3, 1/5, 3 minus 3/5 with a pi outside. Assuming all my calculations are correct, that is the volume of the solid. Okay, volume of this solid. All right, so next example will continue in our next video.